Hello learners, welcome to this course on Embedded System Design using PIC16F877 Microcontroller. So, an embedded system is nothing but a device which can be designed to do a specific operation. Often this device needs to take some real-time inputs and it has to give some feedback to the environment it is going to work on. So it comprises of both hardware as well as a software. So here the hardware, in the sense I am talking about mechanical hardware as well as electronic hardware, and this electronic hardware is controlled by the software embedded into it. So such a device we call it as an embedded system. So we have many such embedded systems like washing machine controller, traffic light systems. In automobiles we have a large amount of sensors interconnected to a microcontroller, and then all the control operations are being performed. In an aerospace system, avionics systems, communication systems, medical electronics, etc. So ultimately an embedded system is a device which is going to do some dedicated operation. So in this course I am going to talk about how to design an embedded system using PIC16F877 microcontroller. So first let us start with understanding the microcontroller. So we will discuss in this tutorial on the features, pin details and the architecture of a PIC16F877 microcontroller. So here PIC16F877 microcontroller is a 8-bit microcontroller. So 8-bit represents, it has an ALU. ALU stands for arithmetic and logical unit, which can perform arithmetic and logical operations on 8-bit data. So if an ALU performs operation on 8-bit data, we say it as a 8-bit microcontroller. If an ALU performs operation on a 16-bit data or 32-bit data or 64-bit data, we call it as a 16-bit microcontroller or 32-bit microcontroller or 64-bit microcontroller. So on what data ALU is going to do the operation, so that determines the type of microcontroller. So here this PIC16F877 is a 8-bit microcontroller, indicates it is going to work on 8-bit data. It is going to do arithmetic and logical operations such as addition, subtraction, logical operations in terms of AND, OR, XOR, NOT operations, etc. So this microcontroller has a 8K by 14 bits of program memory. So 8K represents the number of address locations in the program memory, and in each location it can hold 14 bits of information. So the instruction size of your PIC16F877 microcontroller is going to be of 14 bits. So in each location a single instruction can be stored. It also has a 512 bytes of data memory where we try to store the data. So out of this 512 bytes, 368 bytes is used for normal data operation. Remaining 146 bytes is used for your special function registers. Because we have many peripherals in this microcontroller. So if I want to use a peripheral of the microcontroller, first I need to configure it. So the configuration happens with the help of the special function registers. And during the program execution, the data which resides in the remaining 368 bytes will be utilized. And we also have 256 bytes of EEPROM. So EEPROM is electrically erasable, programmable, read-only memory. So this memory is required to store the values of constants. So something like an ASCII value of alphabets, numbers can be saved in this memory. So whenever I have some constants which can be stored in our microcontroller, that we can store it onto this EEPROM. So we can also store these constants on a program memory, but the problem is if I store it on a program memory, the number of instructions which I can accommodate on the program memory will be less. So thereby we cannot get complex functionality for a particular application. So it is always better to put the constants onto the EEPROM memory. So these memories are built from CMOS flash or EEPROM technology. And this microcontroller comes under your RISC architecture. So RISC architecture in the sense reduced instruction set computers. So reduced instruction set computers in the sense it has less number of instructions. So it has about 35 instructions and most of the instructions are single cycle instruction. It takes only one clock cycle to execute the instruction. Very few instructions like jump, call instructions, it will take more than one clock cycle. So most of the instructions in the instruction set of PIC16F877, it gets executed within single clock cycle. And in addition to that, in RISC architecture, we have less number of addressing modes. So addressing modes are nothing but how a data is accessed by the CPU. So either the data can be in the instruction itself, then it is called as a immediate addressing mode. So if the address of data is specified in the instruction, we say it as a direct addressing mode. If the register has a data and that register is specified in the instruction, we call it as a register addressing mode. Register indirect addressing mode represents a register contains an address of a data. So it supports different addressing modes and the number of addressing modes are less in number in case of a RISC architecture. And also the instruction size is going to be fixed. It is going to be fixed. Here in our case, it is going to be 14 bits of instruction. So a clock frequency of up to 20 megahertz can be supported by the microcontroller. So the microcontroller has an inbuilt clock divider circuit. So whatever clock frequency which we connect, it will be internally divided by 4 and that frequency will be used as a operating frequency of the microcontroller. So for example, if I take a 20 megahertz crystal connected to a microcontroller, it is internally divided by 4, so it becomes 5 megahertz. So the single clock cycle time will be of 1 by 5 megahertz, it will be equal to 0.2 microseconds. So each instruction will take 0.2 microseconds to execute. And the microcontroller, it has 5 I/O ports, input or output ports. It is named as port A, port B, port C, port D, port E. So these I/O ports can be used for interfacing your input or output devices. So in port A, I have 6 pins, RA0 to RA5. In port B, I have 8 pins, RB0 to RB7. In port C, 8 pins, RC0 to RC7. In port D, again 8 pins, RD0 to RD7. In port E, we have 3 pins, RE0 to RE2. So in port A, 6 pins, port B 8, port C 8, port D 8 and port E 3 pins. So altogether we have 33 I/O pins which are configurable. As a programmer, we can configure it for input operation or output operation, and also we can set the pin to be an analog pin or a digital pin. And each port pin can source or sink 25 milliamperes of current. So it can either source in the sense it can deliver 25 milliamperes of current to any output device. Same way from an input device, it can get 25 milliamperes of current. And this port pins support a TTL voltage levels. So in case of an input signal, the TTL voltage levels are low will be treated from 0 volt to 0.8 volt and high will be treated from 2 volt to 5 volt in case of an input signal. If it is an output signal, then the low signal will be taken as 0 to 0.4 volt and high signal will be taken as 2.7 to 5 volt. So it supports TTL voltage level logics. So, and each port pin has multiple functionality. From the pin details, you can see that each pin has multiple functionality. For example, here pin number 5, if I take, it can be used as a digital pin. RA3 is a digital pin. It can also be used as an analog pin. AN stands for analog channel 3, and it can also be used as a reference voltage pin for the ADC. So it has multiple functionality. It can be used as a digital pin, analog pin, or it can be used as a reference pin for your ADC. So similarly, if I take some other pin like RD7 slash PSP7, which means it can be used as a digital port D pin and also parallel slave port pin number 7. So like that, each pin has multiple functionalities. So in order to select a particular functionality for a pin, we need to do the configuration part. So for configuration, we make use of the special function registers. Next, I have a 10-bit analog to digital converters. So analog to digital converters, in short form, it is called as ADCs. So it is very vital in any embedded system design because most of the embedded devices requires the sensor inputs. So the sensors, mostly it will be in analog in nature. There are very few sensors with digital output. Since our microprocessor or a microcontroller is a digital device, we need to provide only digital data. So we need to convert this analog sensor output into a digital data, and hence it can be processed by the microprocessor or a microcontroller. So for that, we need to have an analog to digital converter. So here we have a 10-bit analog to digital converter. So 10-bit represents after conversion process the number of bits we get from the converted process. So we get a 10-bit result from a ADC, and this 10-bit can be processed by the CPU. The resolution of your ADC will be about 4.88 millivolt for a reference voltage of 5 volt. So if I keep a reference voltage of 5 volt, then our input can swing between 0 to 5 volt. So we can also change the reference voltage for the ADC. By changing the reference voltage, I can increase the resolution of your ADC. So resolution is nothing but the smallest voltage change which can be represented as a proper binary output. Smallest voltage change which can be represented as a proper binary output is nothing but the resolution of your ADC. Then we have timers, 3 timers, timer 0, timer 1 and timer 2. So timer is nothing but when I have 2 events separated by an interval. So this interval can be configured, it can be varied. So this interval can be in terms of a millisecond order, microsecond order, second order. So this interval can be varied, and this timing can be used for generating an interrupt. So this interrupt can be used for toggling an LED and for sending information. We can make use of this timing signals. So these are the hardware timers. So the hardware timers, I have 3 in number: 8-bit timer, 2 8-bit timers, timer 0 and timer 2, which means it has a register of 8 bits. And timer 1 is a 16-bit timer. It has a register of 16 bits. So we can load a value onto this timers, and we can do the incrementation of this timer content. The incrementation interval can be varied. It can be programmed. Once the timer overflows, an interrupt can be generated, and this interrupt can be used for controlling the output devices. So here timers can also be configured in 2 modes. One is in timer mode or in counter mode. In timer mode, the incrementation of the register happens with respect to the clock frequency. Whereas in counter mode, the incrementation happens with respect to the external event. If the incrementation happens with respect to an external event, we call it as a counter. If the incrementation of the register content happens with respect to the clock frequency, we say it as a timer. Then we have interrupt. capability. Up to 14 sources of interrupts are supported. So interrupt in the sense any peripheral device, if it wants to utilize the CPU, then it will make a request. Upon request, the CPU can respond to that interrupt by providing the necessary program execution related to that input or output devices. So an interrupt comes from a peripheral device. On receiving that interrupt, the CPU can run a program which is nothing but the interrupt service routine. So it can run a program related to that interrupt, thereby it can service that interrupt. So here we have about 14 sources of interrupt. Like I can have an external interrupt, port B change interrupt, I can have a timer interrupt, I can have a ADC interrupt, serial communication protocol interrupts like I2C interrupt, SPI interrupt, USART interrupt, etc. We have many such sources to create an interrupt. Whenever interrupt is generated, the ISR, interrupt service routine, will get executed. Then we have two pulse width modulation modules. So pulse width modulation in the sense we essentially create a square wave with different duty cycles. So the duty cycles can be varied. It can be changed with the programming. So we have two such modules to generate a pulse width modulation wave. So this is used in many real-time applications to control the speed of a DC motor, to control the angle of your servo motor, etc. So we require a pulse width modulation circuit, and it can be configured to generate different duty cycle square waveforms. These modules are called as CCP modules: capture, compare, and PWM module. So it can be used for PWM signal, or it can be used for capture signal or compare mode. So capture signal in the sense when an event has occurred, that information can be captured. So if we have some event occurrence, at what time the event occurrence has happened, so that can be captured in the capture mode. In compare mode, we can generate a signal after certain time periods. So something like if I want to create a trigger signal after every 10 microsecond, we can do it with the help of a compare mode. So we can generate a trigger signal, periodic trigger signal for every 10 microsecond or 20 microsecond. Again, this time period is configurable. We can change it. So that is what happens in your compare mode. So in compare mode, we can generate the trigger signal for other devices connected to our microcontroller. In capture mode, we can get the information about when the event has happened. So those information can be captured. Then our microcontroller supports in-circuit serial programming. In short form, we call it as ICSP. So here this in-circuit serial programming in the sense we do our program in a computer. So this computer, it holds a compiler which converts your high-level language program into a machine-level language program. Now this machine-level language program, it should be put onto the program memory of your microcontroller. So in order to put the data from your computer to the program memory of your microcontroller, we need to do the programming part. So here I can do the programming in circuit. When the IC is in the circuit itself, we can directly dump the opcode file into the program memory of your microcontroller through pins. So through pins in the sense I have some pins like PGD, PGC, PGM. So PGD is for programming data, PGC is programming clock, PGM is for low voltage programming. So these three pins I can use for putting the opcode file into your program memory of microcontroller. So without removing the IC, I can do the programming part. So that is the advantage of having your ICSP feature. Then the microcontroller also has a watchdog timer with its own RC oscillator. So watchdog timer is very important because when the embedded system is deployed in a real-time scenario, it might run the program infinite number of times. Suppose suddenly if the program goes into an infinite loop, in the sense the system got hanged, in that case the system needs to be reset. So that can be achieved using this watchdog timer. So whenever the program enters into an infinite loop, the timer starts. So the timer waits until the program changes its state. If it is not changing its state within the prescribed time period, then automatically a reset will be provided by this watchdog timer. So a watchdog timer is not used during the programming stage or the development stage. Once everything is developed, if I want to deploy it onto the real-time scenario, we try to enable this watchdog timer, because in a real-time scenario, there is a chance that the program might enter into an infinite loop. In that case, we need to reset the system. So that is taken care by your watchdog timer. And this watchdog timer, it can operate without the help of the external crystal oscillator. It has its own RC oscillator to provide the timing information for the watchdog timer. Then we have a parallel slave port. So I can send 8-bit data at a time using this parallel slave port. And it also supports serial communication protocols such as I2C, SPI protocol, and USART protocol. So I2C is inter-integrated circuits where the data transfer can happen between a master and slave devices. SPI protocol is a serial peripheral interface protocol. Again, in a synchronous mode of communication can be done with the help of a SPI protocol. USART is a universal synchronous asynchronous receiver transmitter, which can be used for communicating the data between the devices in a serial fashion. And our microcontroller, it also supports a power on reset and a brownout reset. So power on reset is something like whenever we switch on the power supply to the microcontroller, so the microcontroller will take some time for the voltage to get stabilized. Once the voltage gets stabilized, the oscillator frequency starts running. So again, the clock pulses needs some time to produce a stabilized output. So during that time, the microcontroller should not execute any instruction. So an automatic reset is applied during those stages. So during the process of voltage stabilization and also during the process of the waveform clock pulse stabilization, a reset is applied. That is called as power on reset. And there is also another reset option, which is brownout reset. So brownout reset in the sense, whenever the voltage drops below a certain threshold voltage, again the microcontroller should not execute the instruction because it might result in a garbage value. So during that time, we need to put the microcontroller in a reset state. So that option is called as a brownout reset. So whenever our input voltage falls below a threshold voltage, a reset operation is being provided. So that is your brownout reset. And the IC requires a supply voltage of 5 volt and it consumes very low power, 0.6 milliampere at 3 volt. So here I show the pin details of your microcontroller. So here I have VDD at pin number 11 and 32, which is a supply voltage, and VSS is the ground lines, pin number 12 and pin number 31. So we will look at these pins in a little bit detail. Now let us discuss about the architecture of your PIC16F877. So on the right side, I show the architecture of your PIC16F877, which I have taken it from the data sheet of the microcontroller. So here I have the ALU, which is the heart of your microcontroller, which is nothing but an arithmetic and logical unit. So it can do arithmetic and logical operations on 8-bit data. So it gets a data from a W register. So W register is also called as a working register. It gets one data from the working register, and the another data, it comes from a RAM memory. Here I have a RAM memory which is of going to be 512 bytes. So out of 512 bytes, 368 bytes for the data storage and 146 bytes for your special function registers. So the second data to the ALU can come through this file register or from an instruction or from the external memory. That is also possible. So once processing is done, once ALU has performed the computation, the result can be stored onto the W register. From W register, it can be loaded onto a RAM memory or an external memory. So here I have a flash memory which is a program memory. So the size of the program memory is going to be 8K by 14. You can see the width of the program memory is 14. Since it is 8K, the number of bits to represent the address is 2 power 13. So 2 power 13 equal to 8K. So we require a 13-bit address, and in each address location we have 14 bits of information, which is nothing but our instruction. So the instruction resides in the program memory. From the program memory, it goes on to the instruction register. So instruction register holds the current instruction which will be executed by the CPU, and then it goes into the decode circuit. So decode circuit in the sense, to find the functionality of the instruction, it should be decoded. And depending upon the functionality, the control signals will be generated with the help of a clock source here, timing generation circuit. So the timing generation circuit is provided with the crystal oscillator. Up to 20 megahertz we can connect it, and the timing generation circuit, it can generate different timing signals. So we have lot of inbuilt functionality like power up timer. So power up timer is something like a timer which runs whenever we switch on the power supply to the microcontroller. The power should be stabilized. So it requires some time. So the timing is generated by this power up timer. So once this power up timer runs out, then the reset operation can be enabled. So that is your power on reset operation. Same way, the oscillator startup timer, it provides the starting time for the oscillator to get stabilized. To produce a stable output, the oscillator startup timer will help. So during the initial time period, the power on reset will be applied so that it will get stabilized. So both power up timer is for power stabilization. It provides the timing for power stabilization. Oscillator startup timer, it provides the time for oscillator stabilization. So during this both the times, a power on reset will be applied so that the microcontroller will be in a reset state. And as I discussed, we have a watchdog timer which runs whenever our program goes into an infinite loop. It will wait for a certain interval. If there is no change in the state, then a reset function will be applied. Then I have a brownout reset. Whenever our input voltage falls below a certain threshold voltage, a reset operation will be initialized. Then I have an in-circuit debugger which can help in debugging our code. So we can check at what line we have error and we can rectify it. So that is possible with the help of an in-circuit debugger. Then it also supports a low voltage programming where we can use a normal 5 volt to do the programming part. So as I talked about the program memory, so program memory is going to be of 8K by 14 bits. So this program memory is divided into pages of 2K. So I have 4 pages, page 0, page 1, page 2, page 3. Each page is going to be of 2K size. In page 0, the first few locations are dedicated for the vector table. So vector table in the sense, certain important operations needs to be serviced by executing a program. So for example, whenever we apply a reset, a certain program needs to be executed. So the starting address of that program will reside in this vector table. For example, for reset operation, the starting address of your reset program will be residing in this location. Same way, if an interrupt occurs, I need to execute some ISR, interrupt service routine. So the starting address of the ISR will reside in this interrupt vector. So like that, first few locations are used as a vector table, and the remaining locations are used for storing your programs in page 0. Page 1, 2K, page 2, 2K, page 3 is also 2K. Since I have a memory of 8K, it needs to be addressed by a 13 bits. So this 13 bits will be given by the program counter. So the program counter points to the address of the next instruction which will be executed by the CPU. It points to the address of, it points to the instruction which will be executing next by the CPU. So, and also we have a 8-level stack memory. So this 8-level stack represents each stack space will be of 13 bits. So we can store the addresses whenever there is a subroutine call or whenever there is an interrupt service routine. We need to save the return address, so that after returning from the ISR or from the called program, we need to go back to our main program. So we need to know the return address. So the return address can be saved in this stack memory. So we have 8-level stacks. So each location I can store 13 bits. So this 13 bit relates, it is equivalent to your address of the program memory. Then we have the data memory, which is 512 bytes. So in 512 bytes, it is divided into banks, bank 0, bank 1, bank 2, bank 3. Each bank can hold 128 bytes. Out of 512 bytes, each bank can hold 128 bytes. So bank 0, 128 bytes, bank 1, 128 bytes, bank 2, 128 bytes, and bank 3, 128 bytes. So a bank selection can be done with the help of the bits in a status register. So in a status register, we have these 3 bits, IRP bit, RP1 and RP0. In case of a direct addressing, we make use of this RP1 and RP0. In case of an indirect addressing, we use this IRP bit. So let us look at this direct addressing and indirect addressing. So direct addressing in the sense, the address of the data is given in the instruction. So in that case, a 7-bit address is provided in the instruction, which represents the location in a particular bank. For example, in bank 0, my data can be in any of this location from 00 to 7F. So the location is specified in the address itself. So 7-bit for address, and remaining 2 bits which is coming from your RP1 and RP0, which is available in the status register, is used for bank selection, whether I am going to use a bank 0, bank 1, bank 2, bank 3. So bank 0 is selected by 00, bank 1 is selected by 01, bank 2 is selected by 10, bank 3 is selected by 11. So a bank selection is taken care by RP1 and RP0, and the location selection in a particular bank is taken care by your address in our instruction, 7-bit address in our instruction. So 7-bit in the sense 2 power 7 is nothing but 128 bytes. So we can access any location in a particular bank. In case of an indirect addressing, so in case of an indirect addressing, we will make use of a register called as FSR register, which is a file select register. So this file select register is a 8-bit register. So we get the 8-bit value from here. So this file select register is going to have an address. So this address points to a location in a memory. For example, the lower 7 bits 0 to 6, it represents the location selection in a particular bank, and the 7th bit from FSR and IRP bit in your status register is used for bank selection. Bank 0, bank 1, bank 2 or bank 3. It can be selected. So in an indirect addressing mode, in my instruction, we will have a register containing an address. So the register which we are going to talk about is FSR, file select register. So this is a 8-bit register. In this 8-bit register, lower 7 bits are used for location selection in a bank, and the 7th bit and IRP bit in your status register is used for bank selection. So if my IRP bit is 1, then bank 2 or bank 3 is selected. If my IRP bit is 0, then bank 0 or bank 1 is selected. So that is how the data can be accessed by the CPU. So either the data we can get it directly from the instruction, or the instruction can contain an address. From address I can select in which bank it is, in which location it is, we can select. That is called as direct addressing. In indirect addressing mode, we make use of a FSR register. So FSR register holds an address. So the lower part of the address provides the location in the bank, and the 7th bit as well as the IRP bit is used for your bank selection. So, and the status, ALU status can also be stored in the status register, like a carry flag can be set, digit carry which is equivalent to auxiliary carry. Whenever I have an overflow from a nibble operation, we say it as a digit carry. Whenever I have an overflow in the byte operation, we say it as a carry, and 0 flag can also be there. If my result turns to be a 0, then 0 flag can be enabled. Then we have 2 more bits, which is timeout bar and PD bar. So timeout bar is for a watchdog timer. Whenever the watchdog timer runs out, it needs to generate a interrupt signal that is indicated by this timeout bar, which is an active low signal. And power down mode is for sleep operation. So we can operate our microcontroller in a power down mode. So that is regarding the operation of your microcontroller. Now let us talk about the peripherals connected in a microcontroller. First, let me start with the ports, I/O ports. As I said, I have 5 ports: port A, port B, port C, port D, port E. In port A, we have 6 pins, RA0 to RA5. So this R represents digital pins. R represents digital pins, RA0 to RA5. And this port A, it also has a multiple functionality, like it is connected to a to D converter. So the channels of the to D converter are specified as AN0, AN1, AN2, AN3 and AN4. Remaining channels are available in the port E. In port E, I have AN5, AN6, AN7. So I have a 8 channel ADC. I can connect 8 inputs to the ADC. So the channels are represented by AN0 to AN7. So port E is also represented by RE0, RE1, RE2. These are digital pins of port E. So port A and port E are connected to the A to D converter, and the reference voltage can also be provided for the A to D converter. So to increase the resolution, I can give our own reference voltage. So that is provided in this pins RA2 and RA3, V reference plus and V reference minus. So there is also a functionality in RA4, which is timer 0 clock input functionality, which can be used for counter operation of timer 0. Then I have a slave select signal for SPI protocol. So SPI protocol, a particular slave needs to be selected. So that can be done by this slave select signal, which is an active low signal. In port E, we have, in addition to digital pins, analog pins, I have other functionalities like read information, write information and chip select. If I connect the external memory, external EEPROM memory, then I need to read a data from that memory, I need to write a data into that memory, and I need to select that memory. So those things can be done with the help of this RD bar, WR bar and chip select signal. Then we have port B, which is an 8-bit port, RB0 to RB7, which indicates digital pins. Then RB0 is multiplexed with the external interrupt pin. So I can connect any peripheral devices which can provide the interrupt to the CPU. So which is an external interrupt pin. Then we have ICSP feature. in-circuit serial programming feature. So in circuit serial programming, I have the programming pins, program clock, program data, and low voltage programming is enabled by this PGM. In port C, again I have 8 digital pins RC0 to RC7, and it is multiplexed with other functionalities like timer 1 functions. So T1 stands for timer 1 functions. CCP modules. CCP modules are capture, compare, and PWM modules. We have 2 in number. So we have CCP1 and CCP2. Same way I have functionalities for your SPI protocol. So SPI protocol is a 4-wired protocol which is used for serial communication. So we have SDO is a serial data output, SDI is serial data input, serial clock, and a slave select signal in the port A. Right? So which is a 4-wired protocol. Serial data output, serial data input, serial clock, and slave select signal. So I2C is a 2-wired protocol. Okay, so I2C, it requires a clock signal which is SCL, serial clock. SDA is a serial data. So SCL and SDA are related to I2C protocol. Again, it can be configured in a master-slave configuration. We also have a USART protocol, serial data transfer using a USART protocol. So there I can use transmitter receiver pins in asynchronous mode. In synchronous mode, I can use it as a clock and data. So in a synchronous mode, we use it as clock and data. In asynchronous mode, we have a transmitter and receiver lines. So port D is multiplexed with your parallel slave port. We can transfer 8-bit data at a time. So PSP0 to PSP7 are the pins for your parallel data transfer through parallel slave port. So these are the ports associated with your PIC16F877 microcontroller. So we have other peripherals like 10-bit A to D converter, 3 timers, timer 0, timer 1, timer 2. So timer 0 and timer 2 are 8-bit timers. Timer 1 is a 16-bit timer. We can configure this timer in timer mode or in a counter mode. So timer mode in the sense, the incrementation of the register happens with respect to the clock frequency. Whereas counter mode, the incrementation of the register happens with respect to external event. Then we have USART, which is universal synchronous asynchronous receiver transmitter. This is all a hardware module inside your microcontroller. Then we have a synchronous serial port, which is I2C protocol and SPI protocol. We have 2 CCP modules, capture, compare, and PWM modules, and there is also a data EEPROM inside your microcontroller. So this is the architecture of your PIC16F877 microcontroller. So in this tutorial, I have discussed about the features, pin details, and architecture of your PIC16F877 microcontroller. Thanks for watching. Please subscribe for more technical learning. Thank you.